job is to understand what actually goes into the Cauchy perspective of where the real numbers come from. How do we get specifically to defining what it means for a sequence of rational numbers? And so we talked about what the definition of a sequence was on Monday, to talk about what it means for that sequence to be said to be convergent. And that if it can be said to be convergent, then its limit is some number which may or may not actually be rational. So when we began the semester, we started with this famous sequence, right? The 0.9, 0.99, 0.999, and so forth. And the reason that we looked at this sequence is that we decided, actually we didn't, you did, you decided that the limit of this sequence, whatever it is, if we could somehow continue this sequence infinitely far, I'm just going to kind of put an infinity in some quotes here, that this limit is going to be a number that we would understand to be the result of adding, quote-unquote, infinitely many nines after this decimal. And so if we can decide what this limit is, then the Cauchy perspective says that that limit is by definition a real number. Whatever real number it happens to be, we know that that limit will exist and will be a real number if this is a convergent sequence. But that's a big if. So where we start off today is deciding what does it take for us to decide that a sequence, in particular today a sequence of rational numbers, what does it take for us to decide that that sequence is convergent? This is a place where you have, and I know because I've read your quizzes and I've read the work you did on exam problems all the way up to this point, you all have some intuition about what this definition is. Because I've seen you use phrases on quizzes and on other problems that you've worked in this class, like closer and closer to, or infinitely close to, or the A word, approaches. All of these are phrases that I've seen people, not just a couple of you, most of you, have written something like this on a quiz up until this point. And I've begun to, in my feedback, say, hey, you know what, this is intuition from calculus. And intuition is not wrong. In all the cases where you were using these phrases, it's something that if we were in a calculus classroom, I would say, yeah, that's an acceptable argument. So this isn't wrong, but it's also not a proof. It doesn't rise to the standard, the burden of proof that we have for ourselves in an upper-level math majors course where we can't take anything for granted. We can't take persuasion, which is what those words are, as a substitute for proof. So our job today is to figure out what is the burden of proof to make this intuition that you have about a sequence like this one, which we decided on Monday gets closer and closer to what number? 1. What's it going to take for us to actually prove that this sequence is convergent and that the limit of that convergent sequence is the real number 1? If we can do that, then at least in the Cauchy perspective, we have settled the mock trial debate from the first week of the course to say that, yes, this is a real number, which gets rid of the objection that Team 3 raised. We don't even know whether this number is real. And furthermore, that this real number is the same as the real number 1, the rational number 1, if you like. So that's the burden of proof. That's where we want to get to. So what I'd like for us to do is to kind of go through this example together, and then we'll begin our work on the fourth packet where we'll get a chance to use this definition and its negation and some other related definitions in some more depth. So let's let A sub n, sometimes I'll write that with curly braces around it. More often I think I won't. So we're going to think of A sub n as a sequence. And again, right now I'm going to say sequence of rational numbers, but it's going to turn out that once we have established the Cauchy perspective, we'll be able to replace the word rational here with real. But let's let A n be a sequence of rational numbers. And, well, let me not say and there. Let me say it this way. We say that A n is convergent. AN is a convergent sequence. So there's the all-important word here, convergent. And moreover, we also say that its limit is L. If So here's the definition that you're to complete. And each one of the yellow symbols, by the way, this one here is an absolute set of absolute value bars. In case that looks like an 11, it's really absolute value bars. Each one of these is an ingredient in this definition. So take a minute and a half or 2 minutes and see if you can pull out of your memory bank how do we arrange these symbols in a way that makes the definition that we want for AN being a convergent sequence whose limit is L. The definition of convergent sequence has 4 clauses, and there's a lot of stuff going on around them, right? There's some quantifiers, there's some absolute value bars, there's some different sets of numbers, there's the naturals, there's possibly the reals, there's some inequality comparisons, there's a lot of stuff. But as I was looking, almost every definition I saw seemed to agree at least on how this definition begins. What did you say was the first clause in this definition? There was unanimous agreement that this definition begins with the clause for all epsilon greater than 0. Okay? I also saw a lot of agreement on what the last clause of this definition was. The conclusion, if you like, the big finish. What did you say was the conclusion of this definition? The thing which if we're going to use this, if we're going to prove that this definition applies to a certain sequence, for example, then this is the clause that we would be using as our burden of proof. What was that concluding clause in your definition? So I saw this one on nearly every paper that I looked at as well, which means you probably have the right one in front of you. The last clause of this definition asserts that the absolute value of the nth term of the sequence subtracted from L, which is our purported limit, right? The absolute value is less than epsilon. That's the last clause. Once, by the way, that we get all the clauses in place, we're going to also kind of reinterpret what they're actually telling us about the sequence. Let's actually start that process now so we don't have to wait too long. When you take the absolute value of the difference between 2 real numbers, what are we really doing there? What are we measuring? The distance, right. That's when we first talked about absolute value. So the distance between the nth term, of the sequence, and the limit L, and the value L, is less than epsilon. Less than epsilon. And we know what epsilon means, right? Because epsilon is the quantity which was chosen by the universe for us in the very first clause of this definition. Right? And so this first clause, if we kind of try to interpret what that's saying, this is saying that no matter, this is another way to kind of think about what a universal quantifier at the beginning of a definition is saying, no matter what positive epsilon is chosen, no matter what positive epsilon is chosen, the distance between the nth term of the sequence and L is less than that epsilon. But there must be some missing information here. We need these couple of clauses in the middle, because without them, what we would be saying is that the distance between the nth term of the sequence and the limit is less than epsilon for any positive epsilon that we choose. But without any additional information, what this is saying is that this distance is smaller than every positive real number. But what's the only possible distance which is smaller than every positive number? Given that distances have to be non-negative, what's the only non-negative number which is smaller than every positive real? 0. So without these middle clauses, what this is forcing is we're forcing the distance between the nth term of the sequence and the limit to be equal to 0. In other words, we're forcing the nth term of the sequence to be equal to the limit, which, as we know, going back to that intuition about closer and closer, approaching, infinitely close to, none of those, well, I'd say all of those, are not capturing the notion of being equal to the limit, but they're capturing somehow this notion of getting arbitrarily close to the limit. So that's why we need some additional clauses here. Without them, we're forcing the sequence to be equal to its limit. So here's maybe the hook that we need to grab onto. This last clause is telling us something about the nth term of the sequence, but it's not telling us where n is coming from. And that's the job of these middle two clauses. So let's look into those. I think the second clause that I saw on most people's sheets was also mostly the same. What did you write for your second clause that can begin to give us a clue as to where this little n, the nth term of the sequence, is coming from in this definition? This was the clause that I saw on a lot of papers. There exists a capital N, which is an element of the natural numbers. So we're somehow getting closer because now we've introduced a natural number into our definition, and we know that this little n, which is still an undefined element of this last clause. We still don't know where this little n is coming from, but at least this little n is going to be a natural number, and now we have some kind of natural number on the table in our definition. Let's kind of interpret what, well, it's kind of hard to interpret what this capital N means until we get the third clause. And this third clause was, I think, the sticky wicket. It's the one that was missing, either knowingly missing or unknowingly missing in most of the versions of this that I saw walking around. And it's the one that's the most opaque when we first look at it. So this is the one I want us to finish this discussion by talking about. Did anybody have a suggestion for what goes in between these three elements that were pretty common in most people's definition? What goes here? What are some ideas? How are we going to relate this capital N, which the definition now asserts exists and is a natural number, and this little n, which we still don't know where it comes from in the conclusion? Without a link that tells us how those two are related, this is still a nonsense definition. Let's come back to this example. So here's an example of a sequence that, if we look at its table of data, its numbers, the values of the sequence, are kind of bouncing around. It starts out at 0, and then it goes up to something positive, then it goes down to something negative, positive, negative, positive, negative. So it has this alternating sequence behavior that you may remember from calculus when we first talked about sequences. But based on the picture and based on the numbers that are in this table, it feels to us, using that calculus intuition of approaching or closer and closer or infinitely close, what is the limit that we think this sequence will have? Looks like, from the data and from the graph, that the limit of the sequence is 0. These numbers are getting smaller and smaller and smaller, and we suspect they will continue to get arbitrarily small so that the limit is 0. And we can see that in this picture by observing that the x-axis, right here, seems to be the horizontal line to which these elements of the sequence are approaching. Now, if we go back to the definition that we're working on for a second, let's get some of our players in this definition onto this new stage. So epsilon, for us, is a distance. It's a distance that we're asserting that the sequence is going to get that close to the limit, no matter how close we want it to get. Right? No matter how close we want the sequence to get to its limit, it will get that close. That's the assertion that we have so far in our definition. So let's suppose, back in this diagram, that we'd like for that distance to be, I don't know, 0.03 or something like that. So now 0.03 is playing the role of my epsilon. So not a here, but epsilon. I just couldn't write epsilon into this grapher. And so in the picture, where that's showing up is it's the radius of this interval. 0.03. That's my epsilon. That's how close I'm asking for this sequence to get to my limit. And my limit is 0, and that shows up as the y coordinate of this horizontal line in the middle of my little band here. So 0, that's my L. 0 is L. It's this mark on the y-axis, if you like, right? Okay. So now let's look at this picture and say, how is it that we know, based on the picture, that the sequence is getting epsilon close to 0? What's actually happening to the dots on my graph as I read from left to right? How can we tell that they're getting epsilon close to 0? Sorry, 0.03 close to 0. Given that the role of 0 here is represented by the horizontal line on the x-axis, the role of the epsilon is the radius of this strip around the x-axis. What's happening to these elements of the sequence? They're going inside of the strip at some point, right? This element right here, this would be the 6th element of the sequence. The 6th element of the sequence is within 0.03 units of 0, because it's inside of this horizontal strip, this orange horizontal strip. And the 7th element is as well. The 8th element is as well. The 9th, the 10th, the 11th, and so on and so on and so on and so on and so on. So here's my question. Which elements of this sequence are epsilon close to L? Not enough for us to say that all elements of the sequence are this close, are epsilon close to L, because that would mean that every one of these blue dots would have to be within that orange strip. And that's not true. But it does seem like there are enough of them that are that close that we'll be able to assert that this is a convergent sequence and the limit is 0. So how would you answer in this particular concrete example, which terms of this sequence are epsilon close to L? I'm saying epsilon close to L because what I'm trying to replicate here is the satisfaction of the inequality an minus L is less than epsilon. Satisfy an minus L is less than epsilon. And what you just told me is that this is true for all n's that are greater than 5. Right? For all n greater than 5, this sequence an satisfies an minus L is less than epsilon. And again, for the particular value, L equals 0 and epsilon equals 0.03. Right? So for L equals 0 and epsilon equals 0.03, it's true that an minus L is less than epsilon for all n greater than 5. And again, the 5 comes up right here. Right? So after we get past the 5th term of the sequence, so here's A5, the 6th term is epsilon close. It's 0.03 close to the limit. The 7th term is also. The 8th term is also. And so on and so on. Right? And so now what we can see is that the missing clause in our definition is something that looks like this. That says that it doesn't have to be the case that every single one of the terms of our sequence is that close to our limit, but there has to come a certain threshold, a certain point, a certain term in the sequence, such that afterwards, once we pass that threshold, once we cross that dividing line, all of the terms in the sequence after that point have to be that close to our limit. The sequence can sort of bounce around, dink around, do whatever it wants to without being close to the limit for a while if it wants to. But after a certain point, it has to get its act together and remain within that strip for the rest of time as we go out towards infinity. So the question that was just asked is, okay, that's the story for this particular value of epsilon, 0.03. But what happens if I pick an epsilon which is bigger or an epsilon which is smaller? Well, let's suppose that we make the epsilon bigger. Then what do we expect to happen with that threshold? Where is that threshold of being epsilon close going to go if I expand my epsilon from 0.03 to, I don't know, 0.2 or something like that? Now where is the threshold after which all the terms of the sequence are epsilon close to the limit? So for this value of epsilon, the threshold occurs much sooner. So here, for all n greater than 0, it's true that the absolute value of an minus L is less than epsilon for epsilon equals 0.2. Right? So when I make my epsilon bigger, the sequence goes into that strip sooner. So that threshold occurs at a lower number. By the way, though, 0 is not a natural number. So if we want to use this with the definition that we're working on, maybe instead of saying greater than 0, how should we rephrase that? That uses a natural number instead of 0. Yeah, how about greater than or equal to 1? 1's a natural number. Right? So because we have a natural number in our definition, this is the route that we're going to go. So instead of using a greater than, we're going to use greater than or equal to. Just so that when the entire sequence is that close, we don't end up with a problem in our definition. So if I make the epsilon bigger, then this number tends to get smaller. And vice versa. If I want to get really, 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 really close to my limit by making epsilon really, really, really small, then what do you think happens to that threshold? Let's say I want to make epsilon 0.01 or something like that, or even smaller than that. So now that I made epsilon super tiny, what's going to happen to that threshold? What's the term after which epsilon, after which these elements go into that strip and never leave. Yeah, it looks like maybe 11. I would say that. So here's the 11th term. Here's the 12th term. And it looks like from the 12th term on, all the rest of the terms in that sequence remain inside of that strip. By the way, terminologically, in case I use these words, and I find that it's occasionally helpful, when we divide up a sequence into a finite number of terms up to a certain point, and then an infinite number of terms after that point, we often say that the first part of that sequence is called the head of the sequence, and the second part of the sequence is called the tail. And the tail of the sequence is always infinite, by assumption, right? It always has infinitely many elements in it, and the head is always finite. So when I say the tail of a sequence, what I'm talking about is all of the terms in that sequence past a certain point. In this example, it's all of them past the 11th. So starting with the 12th and continuing on to infinity, we would say here for all n greater than or equal to 12, it's true that the distance between an and the limit, which happens to be 0, is less than epsilon, which here is 0.01. So the smaller that I make my epsilon, the longer it's probably going to take for my sequence to get that close to my limit. But if this truly is a convergent sequence, and if the limit is what we say it is, then we will always be able to find some point in the sequence after which all the terms of the sequence are that close, as close as we demand that they be. Let's figure out how this fits with the definition that we were writing. So what's missing in here? What is this clause supposed to tell us? It's supposed to tell us that there exists a point in the sequence after which all of the elements in the sequence are as close to L as we want them to be. So looking at what you just wrote about the concrete sequence we were just looking at, how would you complete this third clause? Let's write it in English first. Yeah.
Would it be for all an greater than or equal to capital N?
Yes. Great. I'm actually just going to change one element that what you just said. So you said for all terms in the sequence past that point, except that it's not that the ANs, those are the Y values on the graph, are greater than N. It's the N's, the X values, need to be greater than capital N. So for all N greater than capital N. So again, let's go back and interpret these middle two clauses now, what they're telling us. No matter what positive epsilon is chosen, there is a point in the sequence I don't want to say point. Let me say an index. There is an index in the sequence so that all terms past that index, and I'm going to make one other quick modification here, satisfy that the distance between that term of the sequence and the value L is less than epsilon. And the one last modification I wanted to make is just to make that greater than or equal to there. That way, if the whole sequence satisfies it, then we can still use capital N equal to 1 being a natural number. This is the definition that is going to make the world go round for the next 5 or 6 weeks. Right? And there's a lot. There's 4 different clauses, and 3 of those clauses have logical quantifiers in them. Right? For all epsilon greater than 0, there exists a capital N, which is natural number, such that for all little n that are greater than or equal to that n, it's true that the absolute value of an minus L is less than epsilon. So there's a lot of logical content in here. When it comes to actually writing a proof or finding a counterexample, we have to be attendant to all 3 of these quantifiers at the same time. And that's no mean feat, and that's going to take some practice that we're going to get right away to close out the hour today.